Hello everyone and welcome to lecture today. Today's lecture will be on Greens theorem in the plane, which is one of the most important integral theorems, and as we'll see has several different extensions to 3D. So Greens theorem in the plane is exactly what it sounds like. It's going to be in the plane or for in 2D for a two-dimensional vector field. So let's get into this, and we are going to start by saying we're going to consider what's called a planar vector field, which we've talked about before. Where f can be expressed as, because it's planar, it's two coordinates, p of xy and q of xy. And we tack on a 0 for the third coordinate as well. But really we just want to think of this as a mapping from some domain in two-dimensional space into two-dimensional space, because it's staying inside 2D. And this is, remember, always going to be defined on some set. We'll call the set the domain set, where D is a subset of our R squared of two-dimensional space. And of significant importance to us for this theorem that we'll be talking about is going to be the curl of this vector field F. So recall that when we go to calculate the curl of a vector field in 2D, you can obtain that both of the x coordinate and the y coordinate are 0, and the z coordinate, or the z component of the curl, is the quantity partial derivative of q with respect to x minus the partial derivative of p with respect to y. So the only rotational component this curl can have is around the z-axis, or about the z-axis, when we're considering a vector field it's a planar vector field, specifically the curl only points in the k-hat direction, or the k-hat component of curl is exactly this difference, dq dx minus dp dy. So this idea is going to be very, very important to us. So we'll start with the first statement of Greens theorem. What we're going to do is we're going to say that. So let's let the domain R be a bounded simply connected what this means is basically that it's free of holes. More advanced way of defining simply connected is that any curve C, and this is our domain R, any curve C in R can be continuously shrunk to a point that is contained in R. So this is true for any curve. But this is what simply connected means, that there's essentially no holes in the region R. And R is in general, we'll say, a subset of D. A subset of the domain of our function. This is our first set of assumptions. And then our second assumption is we're going to let the curve C be a piecewise smooth curve, the boundary of the region R. So C is the boundary curve that bounds the region R. Then the statement of Green's theorem is as follows. It's that the accumulation of the flux of the vector field F on the boundary curve C is going to be exactly equal to the accumulation of curl of the vector field F within the region R. It's the interior of the curve C. Oops, and I forgot to put one last assumption up here that is actually very, very, very important. So I'm going to add some space and add it up here. F is differentiable, assumed to be differentiable. In the domain D, for all points in D. And this is important to guarantee us the existence of this curl. So as long as this is true, though, these three assumptions are true, we have that Greens theorem in the plane is saying that the total circulation of the vector field around C is exactly equal to the double integral of the curl of this vector field in 2D. Now, a more standard way of writing this, and this is a much more standard way of seeing this, is to write it as written out in coordinates, in our coordinates. So in this case, this will be the closed contour integral around the boundary of P dx plus Q dy. And remember, if you remember back to our contour integrals lecture, this is an equivalent way of writing the contour integral. It's a completely equivalent notation. And we're going to see that for the proof, when we end up proving Green's theorem, this is going to be a nice notation to be using. And we see that this is going to be exactly equal to, in Cartesian coordinates, the curl of f is dq dx. Or the curl of f dotted with k hat is dq dx minus dp dy. dy dx. Using Cartesian coordinates, dA is just dy dx. So both of these things mean the exact same thing. We're essentially saying that the circulation of the vector field f is equal to the accumulation of curl inside the region. And this is a really, really nice theorem because essentially it's we can think of it as, in some sense, a generalization of the fundamental theorem of calculus from single variable calculus to multivariable calculus, so to vector fields. And this is one of the first main generalizations that we'll see. The idea here is that we're saying, we're equating in some sense a sort of derivative of this vector field f, the curl of the vector field f. We're equating that throughout the boundary, throughout the interior of this region R, to the action of the vector field along a specified direction on the boundary. This is saying the accumulation of the vector field tangent to the boundary is equal to the accumulation of curl over the region inside the region R. And it's also important to point out here that all of these curves are going to be oriented so that we're moving in a specified direction around the curve. So for instance, if this is our curve C and this is our region R, we're always going to be taking our integrals where R lies to the left as you traverse the curve, as you go around the curve. And it's always important to specify this orientation because we know that if you switch the direction of a line integral, you get the negative of that line integral, which will be very, very important coming up. So the proof of this theorem is really, really nice, and it's essentially just broken into two main parts. The first part, we consider what's called a standard domain, which is a simplified kind of domain R. But we'll see very quickly that we can actually generalize this fairly easily. So a standard domain we define as follows. Let's give a definition of a standard domain. I'll draw a picture to help us understand exactly what type of domain a standard domain is. So a standard domain looks like this. It's any domain for which when we draw a line through the domain, we get exactly 2 points of the domain. If I draw a straight line through the domain in either direction, I get exactly 2 intersection points, top and a bottom. And the idea here is that we can solve for a function of the top and a function of the bottom of the domain for any single one of these boundary curves, so to speak. So specifically, we can find, say, a partitioning of our domain. We'll call this point right here and that point right there. Call this point A along the x-axis, and this point B along the y-axis. We'll call this point C along the y-axis, or sorry, these are along the x-axis, these are along the y-axis. Call the bottom C and the top D. So this top function, the top boundary function is a function of x. We'll call y is equal to y2 of x. And the bottom curve right here we'll express as y is equal to y1 of x. So y2 of x is the top of this region. This is valid for x from A to B. And y1 of x is the bottom. And again, this is valid for x from A to B. Likewise, we'll call the left boundary and the right boundary. So this curve right here, the left boundary and the right boundary, we'll call this left curve x is equal to x1 of y, it's a function of y. So we can always find these functions for a standard domain. And then we'll do x is equal to x2 of y for the right side of the domain. You might remember standard domains from your calculus, multivariable calculus class, where you define double integration. This is the first type of domain that you see, the simplest type of domain. So x2 of y is going to be the left boundary function, and x2 or x1 of y, x2 of y, x1 of y is the left boundary function, and x2 of y is the right boundary function. And again, this is for y from, both of these are for y from C to D. And you'll notice that I labeled points here. I'm going to label this point A, this point B, capital A, capital B, this point, the bottom point C, and we'll label up the top point D. Just for help in describing. So we can think of the boundary curve of this region. This is the region, entire region right here is the region R for this simple domain. So the boundary curve of this simple region, we'll call it capital C, like this. May be thought of as the union of the paths ACB and BDA or as the union of the paths DAC and CBD. Right, and it's important to expand upon these paths, kind of expand and remind ourselves that ACB is just the curve y1 of x. The path BDA is the curve y2 of x. But traversed in the opposite direction, so traversed in this direction right here. And likewise, the path DAC is the path x is equal to x1 of x, but traversed in this direction right here, so from D to C. And CBD is the path CBD, so from here to here, which is the path along the curve x equals x2 of x of y. Both these are functions of y. And so noticing this is going to be the key to going through and proving this. So let's go through the first possibility. We'll really look at this in two steps. And step one is to look at this first possibility right here. So ACB and BDA. And we're going to look at the double integral over this region R of the partial derivative of Q with respect to, P with respect to Y. Well, from our rules on double integration, this is the same thing as the integral from A to B of the integral from y1 of x to y2 of x of dp dy dy dx. And we know that p is a function of x and y. This is the partial thing, take the antiderivative of the partial derivative of p with respect to y and evaluate it from y2 to y1. So we know that this is going to be exactly equal to, from the fundamental theorem of calculus in 1D, the value of p at x comma y plus, in general, some general function g of x. That's the antiderivative of the partial derivative of p with respect to y is in general going to be the p of xy plus some arbitrary function g of x. But because we are evaluating this at y2 and y1, this g of x, when we plug in for y here, is going to cancel out in the difference. So this just becomes the integral from a to b of p of x comma y2 of x minus p of x comma y1 of x. And we know from our sum rule we can re-express this as the integral from a to b of p of x comma y2 of x dx minus the integral from a to b of p of x comma y1 of x and this is the key sticking point. What we're going to do is we're going to switch the bounds of integration here because we're trying to get this expression into the form of a closed line integral of this related to this function p right here. And sure enough, we can directly do that. If we reverse the orders of integration here, you notice that this is equal to negative integral from b to a of p of x comma y2 of x dx. Negative sign coming because we reverse the order of integration. This is the integral from a to b of p of x comma y1 of x dx. And this is equal to now negative times the line integral of p dx from b to a, going over this path right here, so going along y2. This is saying go from b to a, where x is b to a and y is y2 of x. That's just that top path. This is just the line integral from b to a along the path b dA. And added to this is going to be this integral right here, which is the line integral from A to B along the path ACB. And so the sum of these two line integrals is the closed loop line integral, or the closed line integral over the entire path C, capital C, of P dx. And so what we've shown is that whenever the conditions of Greens theorem are met for a standard region or simplified region, we have that the double integral of the partial derivative of any function p is the closed line integral around the boundary times -1. So negative the closed line integral around the boundary. And so a good exercise for you to do would be to go through this entire list of equations, right? But for dg dx. Right, so I'm going to say that you should check this next statement. And the calculations are very much the same, almost exactly the same, just with a couple different differences, mainly because the double integral now, you get r of the function d q dx dy dx is going to be exactly equal to the closed line integral, not negative, no negative, the closed line integral of c times q of q dy. So this is a big result, and this is a big result that you should check. It's very similar to the above calculations, just with a couple minor differences, but they're very small differences. And when we now add the first part here, this is step 1, this part will be step 2. When we add the results together, we get exactly what we want, which is that the closed line integral of p dx plus q dy over a boundary curve C is going to be equal to dq dx integral, double integral, plus negative dp dy, double integral, which is the double integral over r of dq dx minus dp dy, or dq dy, dq dx minus dp dy is right. Yep. This is dy dx. And this gives us Greens theorem in the plane. This is a super useful result. But remember this proof, the proof that we've done here, that I've just kind of done out and shown over, only works for a standard domain, or one in which we can express the top and the bottom as a function of the first variable, and the top and the bottom, or the left and the right, as a function of the second variable. Luckily, though, there's no reason to think that we can't somehow extend this, and sure enough, we can. And we can do it in a very nice way. So let's see how to extend this, and we'll do that by drawing a non-standard region. This is definitely a non-standard region because you have not just 2 points of intersection along this line, or any line here that you draw along Y. You have more than 2 points of intersection, and you can see that many other non-standard regions could be possible. In general, for a general region of space, it could be very many intersections. So the idea here is the following. What we do is we'll introduce curve gamma that cuts this non-standard region up into two standard regions. So gamma will be parameterized going up in this direction. So this is this cut gamma. And what we do is we consider what the line integral looks like and what Green's theorem is saying on the two sub-regions, the standard regions. In this case, we'll introduce a curve that is tracing along this first region right here, but doesn't quite touch gamma. It gets very, very close to gamma, and then splinters off. And goes straight up and around. So this first curve is consisting of an outward part. I'm going to call it C1 epsilon. In this inner part, to this line right here, I'm going to call gamma 1 epsilon. And we're going to do the exact same thing for the other piece. Now notice, before we draw the other piece, all curves that we draw have to have this orientation around the curve. It's the starting orientation that we started out with, so it's going around in this direction right here around the curve. Likewise, then we'll introduce a C2 epsilon going around and touching this boundary. Right here. So this is going to be called C2 epsilon, and this curve is gamma 2 epsilon. This straight line portion right here is gamma 2 epsilon, and this curve right here is C2 epsilon. Now it's important to remember that the ultimate boundary curve, the original boundary curve, is the boundary here, C. It's the entire boundary, entirety of the boundary. And the reason that we're calling these curves epsilon is because, or with a subscript of epsilon, is because we're going to define this distance right here. So the distance between gamma 1 epsilon and gamma 2 epsilon, the max distance, we'll define as epsilon. This gap right here is characterized by the value epsilon. And because these regions, each region surrounded by each one of these curves is, we'll call R, this one is R2 epsilon, and this region is R1 epsilon. We have that within each one of these regions, because they're standard regions, we can apply our theorem, Green's theorem. And Green's theorem applies directly from the proof on the previous our previous standard region proof for Green's theorem. So we have that the closed contour integral over C1 epsilon union R1 or gamma 1 epsilon, which is this curve and this curve of f dot dr is equal to the double integral over R1 epsilon of the curl of f dr and likewise for the R2 regions, the second region, we have that the line integral over C2 epsilon union with gamma 2 epsilon, or the line integral over this closed region right here is going to be the double integral of over the region R2 epsilon of the curl of f, and this should be dotted with k. Or just the k hat component of curl of this 2D vector field. And it's important to think about what happens now as epsilon goes to 0. So what happens to these domains when epsilon goes to 0? So specifically, we'll consider what happens when we add these two expressions together and then take this limit as epsilon goes to 0. Specifically, when I add these two expressions together, we get the closed contour integral over C1 epsilon union C2 epsilon union gamma 1 epsilon union gamma 2 epsilon. So it's this is the combination, right, of the closed line integral over this curve right here and this curve right here. Of f dot dr and this is equal to the double integral over the union of the domains R1 and R2. And as epsilon goes to 0, so in this limit, as epsilon goes to 0, this curve gamma 1 epsilon is becoming gamma. This curve gamma 2 epsilon is becoming negative gamma, or gamma traversed in the opposite direction. And the curve C1 epsilon union C2 epsilon is just the curve C. So as epsilon goes to 0, this integral becomes the closed contour integral over the curve C union gamma, where gamma is the split, union the curve negative gamma, or gamma traversed in the opposite direction. And R1 epsilon union R2 epsilon becomes just the set R. The final step here is remembering how to simplify our line integrals. This is the same thing as the closed integral over C of f dot dr plus the open integral over gamma of f dot dr. Then the integral over minus gamma is negative the integral over gamma of f dot dr. All of this is equal to the double integral over the region R of the curl of f. And because these two values are the same value, they cancel out, and what we're left with is that the circulation of f is exactly equal to the double integral of the curl inside this region R, or the closed integral over the closed contour integral of p dx plus q dy over the contour C, the boundary of R, is the double integral over R of the curl of the vector field f dotted with k hat. And there you have it. We've shown how to take the proof for a standard region and extend it now to non-standard regions. So this is a very, very big theorem, very, very powerful theorem, because essentially this is going to allow us to go through and actually generalize this even more. So it turns out that Greens theorem is powerful for a number of different ways, but essentially it's really powerful because it extends the idea of the fundamental theorem of calculus to more than one dimension. This is now to 2D integrals, where we have this nice combination of is dq dx minus dp dy, saying that this combination of this combination of two functions, q and p, of two functions of two variables, if we take the x partial derivative of q minus the y partial derivative of p, we're getting a measurement of the total amount of rotation in the region R. But what this is saying is the accumulation of that rotation is exactly equal to this line integral over the boundary of the region R, which is exactly intuitively the same as the fundamental theorem of calculus in 1D. It's very, very similar to it. So we'll see some more some more extensions of this a little bit later on. But for now, let's focus on an example problem, or a couple example problems, just to see in a couple short steps how useful this can be. So let's say we want to figure out the area of some region. This could be a very, very complicated region in two-dimensional space. In general, this is a hard problem. It's a very difficult integration problem. But it turns out that we can prove that the area of any region R is exactly equal to the boundary, or the line integral over the boundary of that region. Simply it's 1/2 times the closed line integral of negative y dx plus x dy. It's a line integral over C. So very often it's easier to evaluate this line integral than it is to evaluate the double integral, giving the area for that region. And we can directly apply Green's theorem here, because what Green's theorem is going to be is it's going to say, well, we're looking at the closed line integral of negative y over 2 dx plus x over 2 dy. So in Green's theorem, this is our P, and this is our Q, and so this is equal to the double integral over the region R of the partial derivative of Q with respect to x, which is 1/2, minus the partial derivative of P with respect to y, which is negative 1/2. And 1/2 minus negative 1/2 is just 1. This is just the double integral over the region R of 1 dy dx, which is exactly the area of that region. Let's see if we can apply this to see if this is actually making sense, and sure enough, it is definitely making very, very good sense. And we'll use this formula to get the area of an ellipse in a much easier fashion than we normally have to do it. And if you use elliptical coordinates, which are very similar to polar coordinates, it's not that bad. However, what I want to do is avoid doing the double integral. Let's try and think if we can get the area of the ellipse without having to use this double integral. So sure enough, we know that the area of the ellipse is going to be this double integral for the ellipse of 1 dy dx. And you can go through and evaluate that even in Cartesian coordinates if you really want to, but it's not very nice to do in Cartesian coordinates. It's much nicer to do in elliptical coordinates. However, I think it's even nicer to do using this formula that we've just derived in terms of just this line integral. So a single variable integral will give us the area of this ellipse. All we have to do is figure out how to evaluate the line integral, and this is, again, as we've been doing, reliant on the parameterization of the ellipse. So we can parameterize the ellipse. Remember, the ellipse is the equation x over a squared plus y over b squared is equal to 1. The ellipse is parameterized as x is equal to a cosine of t, y is equal to b cosine of t, which means that dx dt on the ellipse is negative a sine of t, and dy dt on the ellipse is, this should be sine. Just like the circle, only without a radius r. This is the x, either semi-major axis or minor axis, and this is the semi-major axis or minor axis, depending on what the relative values of a and b are. So this is the correct parameterization of the ellipse, which means that this is going to then be b times cosine of t. It's a derivative of y with respect to t. This is just valid for t from 0 to 2 pi. And so now when we go through and try to evaluate this line integral from this formula, what we'll get is this area, the area of the ellipse, is going to be equal to the line integral from 0 to 2 pi of negative y over 2 dx, which is negative a sine of t dt. And we also have the dy term, so I'm going to bring the dt out to the outside of this sum, and plus x over 2, which is a cosine of t over 2 dy, which is b cosine of t dt. And at first you might be saying, oh, this is crazy, this is not making this easier at all. But if you look closely at the coefficients here, you're going to see that we have a 1/2 term common, you have negative times negative, you have b times a. So the area of the ellipse is going to be a times b over 2 times the integral from 0 to 2 pi of sine squared of t plus cosine squared of t, which is itself just equal to 1. And when we plug into this, this becomes ab over 2 multiplied by 2 pi And so our final value for the area of the ellipse is just equal to pi times a times b. But we haven't used any double integral at all to evaluate this. We've just used the fact that for this vector field, so for p equals negative y over 2 and q equals x over 2 for that vector field, by Greens theorem, the closed contour integral over any contour of this vector field is going to be the area of that region. So if we restrict ourselves to the ellipse and use the boundary curve, the integration becomes very, very nice, very, very easy. And this is typically, right, one of the typical uses of Greens theorem is to simplify integration. Right? We might have the integration of a very, very complicated vector field. The double integral could be very complicated to evaluate, and if we do Greens theorem on it, we might be able to show that the line integral is much easier to evaluate. And you could have the opposite problem. For some functions, you might have a vector field where the line integral is looking like it's impossible to evaluate, but when you use Greens theorem to translate it into a double integral, the curl of the function could be very simple. It might simplify so that the double integral might be easier to evaluate. So Green's theorem is a very, very useful tool in that regard, and those are the two main big reasons that it's used for. We can also use it to prove things about curves, so prove certain physical properties, maybe about curves, or about the properties of curves that we've talked about before. So for my next example, I'll show. You remember, for any curve, we can define the unit tangent vector. We can show that for a closed curve, the line integral of on the closed curve C of the tangent vector to the curve is equal to 0. So for a closed curve, if you consider the circulation of the tangent vector field to the curve, this will always end up being equal to 0. So why is this? Well, we have two different ways of showing this. And I'll verify this in both ways, so you can kind of see how to do it in both ways. The first way, remember that the closed line integral of the tangent vector to a curve is the same thing as, if you remember the definition of the tangent vector to the curve, it's the derivative of the position vector with respect to arc length. So this is the same thing then as the line integral of dr, which is the same thing as the line integral over C. Dr is I hat dx plus j hat dy. That's the sum of two separate line integrals, and for each of these line integrals you have the integral of 1 dx by Greens theorem is the same thing as the double integral over the region control covered by C of negative the partial derivative with respect to y of the constant function 1. And the derivative of a constant is 0, so this is going to be equal to 0. And likewise for this integral, you have the exact same thing, only it's dq dx, and q here is 1. So both of these integrals are 0. This is going to be 0, and this is going to be 0. And therefore we've shown that exactly what we want to show. This is method 1 using Greens theorem. We don't need to use Greens theorem. This would be possible to do without Greens theorem, and I just want to show a different method of showing this, just for illustrativeness and kind of showing that There are typically in mathematics multiple ways of going through and getting the solution to a given problem. Remember that any line integral be evaluated from 0 or from A to B, where B is the beginning point and A is the beginning point and B is the end point. In this case, this is going to be t hat, which we know is r prime of t divided by the magnitude of r prime of t. And ds, remember, is going to be the magnitude of r prime of t, dt, when we go to evaluate this. These two magnitudes cancel one another out, leaving for us the integral from a to b of r prime of t dt, which by the fundamental theorem of calculus, in each component of this vector will be exactly r of b minus r of a. And because this is a closed curve C, r of b is equal to r of a. So this line integral is equal to 0. So this is just a nice example, just kind of showing that typically there are multiple different ways of proving something in mathematics. It all just depends on what method you want to use, but Green's theorem is a nice way of showing this. So the next thing I want to talk about in this lecture will be how to extend Green's theorem to more complicated domains. And specifically, this is domains with holes in them, so non simply connected domains. And we know that from some of the examples that we've seen already that simply connected domains are a very important thing to think about, because we've seen certain examples of vector fields defined on non-simply connected domains that are very kind of tricky to deal with. So the question how to extend Green's theorem to non-simply connected domains. And the idea here, and the way that we're going to do this, is the following. So let's take a general domain. R. And we'll just put one hole in R. So I'm going to call the curve that traverses R C, capital C, and this is traversing R in the counterclockwise direction, just like all of our other traversals before. And R is all of this space right here. And this hole I'll call, I should say the contour around this hole I'll call C1. And I'm going to traverse this hole in the opposite direction. Right, this is important here, and you'll see why in a second. Because the trick that we're going to use is the following. It's going to be a similar trick to what we did before. I'm going to trace, and I'm going to form a cut here. We'll form a cut right here, and we'll call this cut trace. In this direction, gamma. So we cut our domain R, and we cut right into that hole. And I'm going to define the following. I'll define path from here all the way around, tracing this region. To be C1 epsilon, or sorry, not C1 epsilon, we'll just call it C epsilon. And then we continue this tracing in here until we cut, and I'll call this gamma 1 epsilon, this piece. And then we have another piece going around the curve, around this in the opposite direction. And we call this portion C1 epsilon. And then lastly, we have one final piece that we'll call this final piece gamma 2 epsilon. And now the trick here, and the amazing thing here that happens, is if we consider the union of C epsilon with gamma 1 epsilon, gamma 2 epsilon, and C1 epsilon. This region, right, this is a closed curve surrounding a region R. Not R, but it's a little bit smaller than R, so surrounding a region R epsilon with no holes. Now, if you consider all of this space right here, there's no holes in this region right here that's surrounded by this blue curve. And therefore, we can apply Greens theorem to this region right here. Specifically, we can consider the line integral, closed line integral over this entire curve of f dot dr, and this is going to be exactly equal to the double integral over r epsilon of the curl of f. And just like before, what we're going to do is we're going to consider the limit as epsilon goes to 0. And as epsilon goes to 0, gamma 1 epsilon becomes just the curve gamma, which is that cut that we defined initially. As does gamma 2 epsilon. But gamma 2 epsilon becomes gamma traversed in the opposite direction. Because of the fact that on the blue curve we traverse like this on gamma 1 epsilon and like this, the opposite direction on gamma 2 epsilon. The curve C epsilon becomes just the curve C because these boundary points match up as epsilon goes to 0. The curve C1 epsilon becomes C1. And lastly, the domain R epsilon just becomes the normal domain R because all of these points that are removed in this cut go away, or they're absorbed as the curves gamma 1 and gamma 2 come together. So from an integration standpoint, then this integral becomes the same thing as the closed surface integral over C union gamma union negative gamma union C1 and this is going to become the double integral over R of the curl of f dot dr or dA. So just like before, this will actually simplify a little bit. It's the closed integral over C of f dot dr plus closed integral over gamma of f dot dr minus the closed integral over gamma of f dot dr, because the integral over gamma is negative gamma is the same thing as negative times the integral over gamma, because negative gamma is just gamma traversed in the opposite direction, plus the integral over C1 of f dot dr. This entire thing is equal to the double integral of the curl of the vector field f dotted with dA. And actually I should say, well, dA you can think of as a vector quantity if you want. This is k dA, but this is dotted with k hat dA. And it's the same thing down here. This is how I typically like writing it. So just like before, these two integrals are the same thing. And what's interesting here is that we have this integral does not vanish. This is saying that the circulation around any curve C of f dot dr plus the closed circle contour integral around C1 of f dot dr. So this sum is equal to the double integral of the curl of f over the region R. So this is the correct form for Green's theorem in the plane when you have a region with holes, so you have a region that's not simply connected. And this actually explains a number of different things. Specifically, in a second, we'll use it to explain the example that popped up a couple lectures ago. So specifically, another nice way of writing this would be that for any boundary contour C, if your region has one hole in it, then the line integral, the circulation around the vector field F around that C is going to be the double integral of the curl in your region minus the integral of f dot cr, f dot dr over C1, where C1 is a closed contour that surrounds that, or the boundary that surrounds that hole. And C1 is traversed in the opposite direction, so it's the clockwise direction, whereas C is traversed in the counterclockwise direction. So this is Green's theorem. So R has one hole. And as you might readily consider, what if it has multiple holes? So it's topologically possibly very complex. You'll get a very similar formula. If it has n, you just need to do this process, this cutting process, for each new hole, for each new individual point that's removed from the region R. So the formula that you end up getting is going to be very, very similar to the one we just got, only you're going to have a summation of different line integrals that you have to evaluate here. Specifically, you'll have to subtract out around each individual missing portion of the domain. You'll have a contour Ci, which is traversed in the clockwise direction, and you have to sum over each one of them for I from 1 to n. And this is going to be the flux, or this circulation around the the larger contour. So the main boundary contour C looks like this, and then for your region here you'll have C1, say, C2, C3, and so on and so forth. So you'll have to compute an integral around each one of these subcontours and subtract it from the double integral of the curl in the region R to do the general Greens theorem. I'm not going to go through and prove this. The proof is almost exactly the same as the proof of this one hole theorem, and you can actually see it in the book as well. But so let's apply this to that example problem, and I'm not going to go through and recalculate things, but if you remember, for the vector field F, from R2 minus the origin to R2, this is the vector field F is equal to x over, or negative y over x squared plus y squared and x over x squared plus y squared we computed that for a circle of radius epsilon over a small circle of radius epsilon, so the line integral is equal to 2 pi. So this is a circle of radius epsilon. The line integral over C epsilon, and this is in the counterclockwise direction, was 2 pi. So if we reverse the orientation, so we say C epsilon is the circle in this direction right here. So in the clockwise direction, the contour integral over C epsilon of F dot dr is going to be equal to negative 2 pi. And now if we consider any other curve that we want surrounding the origin, call this our curve C. This more advanced version of Green's theorem, by the way, remember that we found that the curl of this vector field on its domain here is equal to 0. So for any other curve C, from our second form of Green's theorem, the flux, or the circulation around the curve C of F dot dr is going to be equal to the double integral over R of the curl of F dr minus the integral of c epsilon of f dot dr. This is from the version of Green's theorem that we just proved for a domain with holes in it. Well, the curl of this vector field on the region R itself is 0 everywhere. So this is going to be 0, entire integral. And the line integral of f dot dr computed in the reverse direction, so in this direction right here, is going to be negative 2 pi. So the closed contour integral over C along any curve by Green's theorem is going to be equal to the constant 2 pi, or the circulation of this vector field around any curve, no matter how complicated it is, will be 2 pi. And you can take the limit here. Right? Epsilon here is arbitrary, so you can go as small as you want for epsilon. And this is just exaggerated in this picture right here. But this is explaining for us where that 2 pi is coming from, and why, in general, for a vector field that is curl-free or irrotational, it's not always conservative, because directly because of this result, this extension of Green's theorem. So the idea of topology is very important when we're discussing theorems in regards to vector fields. The last thing that I want to point out is that there are actually two equivalent formulations of Green's theorem in the plane. The formulation we've related to curl, but it turns out we can also relate this to divergence. So we have what's called the curl form and the divergence form of Green's theorem in the plane. And sometimes this is useful, actually, even in just like applications, specifically considering like the flux out of a given region in two-dimensional space, in 2D space. But we're going to see that there's an even bigger application and reason that we're going to kind of point this out right now, because it's very useful when we go to extend Green's theorem in the plane to three-dimensional space, to 3D. So let's assume we have a region R with no holes in it, could have holes in it. We know that we can define the unit tangent vector to the boundary curve R. We can also define the unit normal vector to t hat, as we've talked about. And for a 2D curve, defining n hat is actually very, very straightforward. You can get it very, very nicely directly from t, actually. We know that t hat is equal to dr ds, or the derivative of position along the curve with respect to arc length, which is dx ds dy ds. We know that the normal vector to this curve is going to be at a 90-degree angle to t hat at every single point. So you can ask yourself, what is the vector that is always going to be at a 90-degree angle to this t hat? What I'll do is actually simplify it. I'll use subscript notation for the derivative here, just to simplify our expression here. I'll let you think about that for a second, but if we define the vector n hat, it's going to be a 90-degree angle to t hat, so it has to be perpendicular and point outwards. n hat was going to be exactly equal to the vector ys negative xs. Remember, our orientation here is a counterclockwise orientation. So the vector ys negative xs will be a 90-degree angle, and it will be point perpendicular to t hat in the direction of the outward normal. You can go through and show that they're perpendicular directly by taking the dot product. It's going to be xs times ys minus xs times ys, which is equal to 0. So what we'll also do is we'll define the vector field. So we have the vector field F already, which is the vector field PQ. I'm going to also define the vector field G, which is the vector field Q negative P. And it should be clear to you that if we take the dot product of F with T, this is the exact same thing as the dot product of G with N. It's just equal to P times XS plus Q times YS. And in what we're about to do, it's important to also note that curl of the vector field F dotted with K hat, which is equal to dq dx minus dp dy, is the same thing as the divergence of G. You should check all of these. I want you to go through and just check to make sure that all of these things that I've written down check out and are correct, but I guarantee they are definitely correct. You can see that directly it'll just be x derivative of G is dq dx plus the y derivative of G, which is negative dp dy. Right, so this is exactly a direct kind of check right there that I just did. So we keep all of this in mind and remember that the Greens theorem in the plane, in terms of its vector notation, we've been writing it as the contour integral of over C of F dot T hat ds, or F dot dr, and this is the same thing as the double integral over the region R of the curl of the vector field F dotted with K hat dA. This is the curl form of Green's theorem. Using these nice things we've shown right here, we can also write an equivalent form to this first form as the contour integral of G dot N ds, the closed contour integral of g dot n, is equal to the double integral over r of the divergence of g dA. This is sometimes called the divergence form of Green's theorem. And this is special because the idea here is that this divergence form of Green's theorem is actually giving us something very nice. Because remember, p and q are completely arbitrary functions. So the idea is that if this is true for q and p, which are arbitrary functions, this can be true for any vector field g. And the point is that, right, fundamentally these two things are expressing the same relationship, but they're expressing it in different ways. The curl form of Green's theorem is saying that the total circulation around any closed curve of a vector field f is exactly equal to the accumulation of curl inside the region R. The divergence form of Green's theorem is saying that the total flux of the vector field normal to the curve C, so the stretching of the vector field normal to the curve C, is exactly equal to the accumulation of divergence inside the region R. So the accumulation of stretching of the vector field inside the region R. So that both of these forms are equivalent in the plane. You can use either form in. They're essentially telling you the same thing in the plane. If you use the fact that f is equal to or related to g through this relationship. But we're going to see that there's a very nice expression here, in 3D when we go to extend Green's theorem. So these two forms, I'll write this down. Are equivalent in the plane. However, each has its own unique extension to 3D. And this is what we'll be moving into in the next few lectures. Right? The extension of Green's theorem into 3 dimensions. The first form is called in 3D Stokes theorem. And in 3D, the second form is called the Divergence theorem, or Gauss's theorem. And they're both very special, very much more general things or theorems that help us very much when simplifying and when going through and computing integrals. So I'll end with one final example, and this example is going to show the power of the divergence form. And both of these forms, the curl form and the divergence form, are very helpful in terms of getting simplifications. So the one of the big collection of simplifications for vector fields that are very useful are called the Greens Identities. And we're just going to go through right now, and I'll prove the first Greens identity, which is a super useful formula relating that we can directly prove using Greens theorem. This is saying that for a region R, the divergence of a function f times the gradient of some function g the double integral of this over region R is going to be exactly equal to the closed contour integral over its boundary of f, which is the function f, times partial g partial n ds. So the accumulation of this integral right here, where dg dn is just the normal derivative of the function g, or I should say the directional derivative in the normal direction of the function g. So to prove this, we're going to apply Green's first identity. Sorry, not Green's first identity. We're going to prove Green's first identity. We're going to apply Green's theorem in divergence form. With g equal to the function f times the gradient of g. In which case, this integral that we start with, this double integral, just becomes equal to the closed contour integral over C of the vector field G, because this is the vector field capital G, and by the divergent form of Green's theorem, the double integral of the divergence of G will be equal to the dot product of G with n hat. This is going to be G, which is f times the gradient of G dot product with n hat ds. That's the contour integral of this, which is the same thing as the closed contour integral of f times the gradient of G dotted with n hat, which is exactly equal to the closed contour integral over C of f times partial g partial n, because this is the definition of the directional derivative in the direction n. And this concludes the proof of Green's first identity. So what you might be interested in doing, and what I recommend doing, is going through and checking Green's other identities for yourself. It'd be a very good, useful, a useful kind of practice tool to go through and do. So look at the second identities and the third identities, and see if you can go through and use Green's theorem to prove these identities. But thank you very much for coming to lecture today. I hope you learned something and had a great day.